ago, we noticed that when we're walking with a beverage, it sloshes all over the place. And we see that the faster we walk, the more it sloshes. And if we're riding on a horse, then we notice that it's completely spilled all over the place. So we come up with some kind of a naive conception that any kind of motion causes this kind of an effect. And you intuitively see that the faster the motion, the greater the effect. Now this was what people pretty much assumed until around the time of Galileo. If you try to modulate the motion that's unnecessary, that has nothing to do with the actual motion and straight along. For example, if you're jumping up and down on a horse and so on, then the smoother you go, the less the effect will be. And of course, today we have an intuition developed from being in cars and trains that move at 50 and 100 miles an hour, and in planes at 500 miles an hour. We can walk down the aisle with a cup of liquid, sit down in our seat, and if we weren't looking outside, we wouldn't know that we were moving. We certainly wouldn't be able to tell the difference between moving at 50 miles an hour or 100 miles an hour. And so we developed the notion of an inertial, uniformly moving frame, a uniformly moving state, and we know that they are indistinguishable from each other. We also know that in fact they're indistinguishable from a stationary frame. There's no difference between standing still and holding a cup or moving at 50 miles an hour or 10,000 miles an hour, neglecting any kind of air resistance effect and so on. There's a principle in physics, which is kind of a heuristic principle, but if things are indistinguishable, they're identical. If you can't measure the distinction between two things, between two states, there's no physical meaning to saying that these two states are different. They just have the same values. If they're completely identical in measurement, then they're identical in nature. And so if you have two frames moving with uniform motion relative one to the other, and you cannot distinguish between the two, then you identify those states. And the same thing with stationary. So you consider all inertial states to be fundamentally identical. There's certainly no difference between states moving at 50 or 100 miles an hour or 10,000 miles an hour, nor is there any reason to distinguish between them and a so-called stationary frame, because one person's stationary frame is another person's moving frame. So we say that they are all indistinguishable and therefore identical. Now, of course, one can ask, even in uniformly moving frames, we could be in a plane and we're moving at 500 miles an hour, and it's true we don't notice any sloshing, but maybe if we turn on some kind of electric device, the electric device works differently because it's in motion at 500 miles an hour. So it's certainly conceivable that some physical effects will be different and motion dependent. So this is something, of course, that you have to test. Eventually people test it and come up with some kind of principle and say, no, there are no measurable effects to inertial motion. All inertial states are identical, and you cannot in any way consider one particular frame to be moving and the other one stationary. this is our more modern day notion of inertia. In order to conflate all the examples that I gave, not only indistinguishability of uniform motion, but also uniform motion and stationary. So we don't want to talk about inertially moving frames because it's not necessarily moving. We'll just call it inertial frames or inertial states.
And so we may as well just use inertial, and leave it up to each observer to choose their frame and call it what they wish from that perspective. Some may call that inertial object stationary, some may call it moving uniformly, some at 5 mph, some at 1 million mph.